Welcome to lecture 11, which is on 3D mapping. Once we have the height data, how to represent that height data into a digital elevation model, digital terrain model and digital surface model. So you are going to learn in this lecture what is the basic difference between the three term which is used here, and how you are going to create and what are the applications of these you are going to learn in the lecture. So let us begin lecture. When we are doing planimetric mapping or topographical mapping, we are showing everything in the 2 dimension. So we are preparing a paper map. So when you deal with those paper maps, you see the 2-dimensional paper maps are depicting the 3-dimensional object on the earth surface. When you are doing the topographical mapping, you are drawing the contours. So these contours you are reading in order to understand the ups and downs on the ground. They are shown by the brown color here, and particularly the contours are very dense with the different shapes and orientation in the hilly region. So it takes a while to understand the topography of the ground with the help of such contours which are representing the 3rd dimension on the ground, and also determination of the slope and the profile of the ground. So if we look at the terrain in the 2 dimension on a map, you have contours which are drawn and depicting the 3rd dimension, and lat long lines which are depicting the xy coordinates of that. But normally on the ground, when we look at the same terrain, it looks like in the 3D form the profile. We can see where the vertical cut is, we can see the valley, the mountains, the higher regions. So there is a difference what we actually see on the ground, 3rd dimension terrain, and on the map, topographical map, the same terrain on the topographical map, and it requires the experience actually in order to understand this. So in mountain areas, as I told, that the contours are very dense to each other. So you have eccentric kind of a contours, several contours. So you have to understand which is the highest point, which direction the slope is going, and which are the valley areas. When you are using this map for some design purpose, in order to identify the flat land, in order to identify the gentle slope land, you are taking help of such kind of a maps. But if I represent these contours which are shown on the map in the digital form, I digitize them together, I convert into the digital form, so then I can create a 3D elevation models. I can visualize the whole area on my computer screen. So I can see the ground as I normally see it on the ground on my computer screen. So in the virtual model, the planning becomes much more easy. I can understand the topography of the ground very clearly. So this is what we are exactly doing here. We are converting those height values and the elevation values into digital elevation model. So what that digital elevation model is, a short form is DEM. This is the basic data which is based on the terrain elevation observations. So we know various methods, we know photogrammetric method also to determine the elevation of the various points. So if I know the elevation of the various points, and if I know planimetric coordinates which are the x and y coordinates, then I can determine the digital elevation model as shown in the pictorial form. So in the pictorial form, what we see is the darker gray shades are those areas which are at a lower elevations, while the whiter areas are those areas which are at a higher elevation. So I can actually little bit understand with the help of these shades the digital elevation model, but I can understand it more clearly when I show it in the 3rd dimension. So I can create this kind of a digital elevation model which is a representation of the x, y and z coordinates in the digital mode, I can use contours, digitize them from the available maps. I can use some ground based surveying methods in order to collect XYZ coordinates of the various points and create DEM. Photogrammetric methods where we are using the stereo capabilities of the photographs, simple devices or digital photogrammetric methods which we will learn in the next lecture, or airborne LiDAR survey which will directly give you x, y and z coordinates, point cloud data of the various ground points, laser altimetry, satellite data, stereo data similar to the aerial photography stereo data, or it could be a radar data. So, there are different ways and different approaches by which we can create a digital elevation model. Here we are learning that how the photogrammetric methods are used for data capture, for deriving the digital elevation model. So, the basic definition of the DEM, as you can see the various gray shades which are present in this picture here, it is representing actually the topography of the ground in terms of its coordinate system x, y and z coordinate system on a regular grid basis. So, the whole area has been divided into small grids and each grid now has x, y and z associated with it, and that z value is the elevation value of the ground. So, these are all the interpolated values in each grid using few elevation values. So, if I have few elevation values in the area, I can do the interpolation work using the capability of the photogrammetric software. When we define the DEM, how we define it? It is a bare earth raster grid surface to a vertical datum. We are using this vertical datum, maybe mean sea level, it could be a WGS84 on which all the GPS systems are working, and very useful whenever we are dealing with some study related to the hydrology. We want to determine the flow direction of the water, we want to carry out some land use planning, we want to carry out some urban planning, some alignment survey. So, this kind of digital data is very useful to us. Now, the second term here is digital terrain model, DTM. So, digital terrain model and digital elevation model, they have been used interchangeably in many literature. There is not a big difference between the two here, but the DTM further augmenting the digital elevation model data. What is represented in the DTM? DTM represent x, y and z coordinates of the data along with the feature. Now, those feature could be like the river point, the valley area, the ridge path, the break lines, etc. So, it is showing the natural feature, the top, the ridge line, the valley line in addition to the x, y and z coordinates. So, in a way it is augmenting the data which is already available to us in digital environment in the form of a DEM. Now, the important point is to be remembered is a DTM may be interpolated to generate a DEM, but not the vice versa. So, you can create a DTM from a DEM, but it is not the other way around. Now, building, vegetation cover and other man-made features are removed from this. So, you are not actually showing all those features on the terrain model, and this terrain model is very useful in large number of earth surface planning projects or engineering projects. They are very useful. Look at the DTM. So, this is a DTM when I am showing a 3-dimensional earth surface or a piece of the terrain. So this is again on the grid basis. Each grid has a elevation data, plus also we can see a ridge line is depicted, a valley line is depicted on the data. So we can have a feeling of the ups and downs, true representation, three-dimensional representation of the earth. And this DTM now, I can actually see from a different angle. The terrain would look like different when I change the view height, when I change the view angle. So if I look at the same terrain from a certain height from aircraft, it will look like different. When I see it on the ground, it will look like different. If I change my view angle direction, if I look at from the south or look at from the northeast, it will look like different to me. So view angle and view height is also very, very important whenever we are representing the digital terrain model of the area. So if we look at the bottom figure also, we can have immediately the feeling of the lower area and feeling of the higher ground with this DTM. The third terminology is digital surface model, DSM. And now when we are talking of the earth surface, we are talking of the objects now which are present on the earth surface. We know that there are various kinds of objects with different heights which are present. It could be a tree, it could be a telephone line, it could be a building, it could be a bridge. So any object which is present on the earth surface has a certain height, and if I can show that, if I can overlay over my DEM those height of the object also, then the resulting model is called DSM. So it is displaying any existing surface shapes and the structures which are present on the ground. It is very, very useful. DSM is very useful for large number of projects, maybe it's a telecommunication project, or whether we are talking of the smart city or 3D city models, urban planning, aviation. So for large number of application, it is very useful. You can see in the figure here that each of the structure has been shown on the top of the digital elevation model with the respect height. So this gives us much more clarity in order to understand the basic difference between a DSM and a DTM. So I am showing you here a profile of the terrain, and on the terrain there are some features, there are some buildings, high-rise building, low-rise building, and there are some trees which are present in the area. So if you follow the red line which is marked here, this is the red line which has been marked throughout to show the outline. What you see here, this is called DSM, digital surface model. So if you are showing the elevations of the different objects also which are present on the ground. But if you follow the green line here, which is depicting the elevation with respect to some datum of the ground, the profile of the ground. So this is called a digital terrain model. So we are determining both, we are creating both through the photogrammetric techniques and other methods, so that depending upon our requirement and depending upon the application, we could use them. So if you look at the DSM at 1 meter resolution, that means any object which is 1 meter by 1 meter on the ground is shown here, depicted here. So its 1 meter resolution is shown the DSM, where all the structures, buildings are shown here, and this is the digital terrain model which is shown of the same area. So there is a difference as far as the amount of information content is there. DSM is much more readable in order to understand the features with the different heights which are present on the ground as compared to the digital terrain model. Now we are using stereo-photogrammetric approach for creating the DEM, and then we can create the DTM and DSM also. So we have a manually approach, and we have the automated approach. So in the manual approach, we have already learned how to use those stereo photographs, and also in place of the parallax bar and the stereoscope, further development is using some kind of a analytical instrument along with the stereo plotter. So we are using actually these devices manually in order to determine the coordinates, the height of the various points, and doing certain computations also manually. So this is a complete manual based method where we are using some analytical instrument, where we are using the parallax bar and the stereoscope in order to determine the height of the various points. But now, as the technology is changing, we have the digital methods, we have the automated methods where stereo images we can derive the stereo model and then carry out the measurements also using the capability of the software. So those automated methods are nowadays available. So once, whichever method we used, once we know x, y and z coordinates of the points, we can create a DEM. So very first step when we are creating the DEM would be creating a TIN model. TIN is a triangular irregular network model that has to be created. So this is a very simple. I have the elevation of various points in the area. So if I join those various points together, it will be a network of the triangles. The smallest figure will be triangle, and it will be a network of the connected triangle, and that particular figure is called the TIN model. So in the TIN model, if I take a triangle and all the 3 points of the triangle, I know the elevations of those 3 points, and using these elevation value I am trying to interpolate the values at desired point on the surface or at desired interval. So my next step would be a grid set size will be defined. So I am dividing my area into the grid cell size, and within each grid now the value will be interpolated. So there are various interpolation methods available. So we are using those methods in order to carry out the interpolation of the values which are not available within that grid. So using few values through which we have made a TIN, now we are dividing the whole area into grid cells and then computing the value within each grid cell, elevation values. And now once I have the gridded values which are representing the elevation as well as the coordinates, because it has the line and the columns. So each grid will have 3-dimensional coordinates. I can use these 3-dimensional coordinates to create digital elevation model in the area. So this is the flow diagram which indicates basically the scientific approach which we are using from aerial photography or maybe the stereo satellite images we have. So we are using that, and we are using certain control points, maybe this will come from the GPS, so that we can check the accuracy of the DEM. We can take certain control points also. As we know, in leveling the requirement is the elevation of few points should be known to us. So similarly here there are certain control points required so that we can take the elevation of that and create the DEM, and also there are certain control points which are for cross checking the area. So we are using triangulation principle, and when we are using in photogrammetry it is called the arrow triangulation principle. So we are using that principle. We are doing the orientation of the left photo and the right photo as you have learnt manually the orientation of a stereo pair. Similarly we are doing the right photo and the left photograph, the inner orientation, relative orientation and absolute orientation in the system, photogrammetric system. And then we are ultimately doing the image matching process and creating the DEM. So this is all the scientific procedure which we are using when we are developing the DEM with the help of the digital devices. So this shows different points. The dot 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 are those points whose elevations are known to us. Known to us means we have determined the elevation of such points using the photogrammetric approach. So once we know the elevations, then there are several ways, numerical representations of these elevation data, and one could be the raster form or the gridded form. So this is a raster form and the gridded form. You can't see the each and every grid here because they are dense. So but if I zoom this particular figure on the computer screen, then now you see the each and every grid here. Then that grid actually has been created from the tin. This is tin called the vector model. So there are two models, a vector based model and the raster based model, in order to represent the data. So dot dot, the red dots are those points in the vector based model whose elevations are known to me. So I know the elevations of those points. The algorithm will join them together and this will becomes the triangular irregular network figure. Irregular is that different triangles have the different shape and size, and then this is a grid based model, and then you can create the contour maps also. Like in a topographical map, you have the contours and you can generate the flow line for your application part. So these are the representations of the model. So we are talking about the tin. So it is a vector based model here, and so what we are doing is basically using those elevation values which have been measured, and with the help of that we are trying to interpolate. We are using the interpolation based approaches to carry out a grid based analysis. We can actually also draw the contouring from this data as we do by a normal surveying method. So grid based method, let me explain you further. When the data is stored as a elevation matrix, so this is a elevation matrix. I am taking a small sample here just to explain you the process. So here different values which you see, they are the elevation values, and each grid can be located by its line number and by its column number. So this is like a matrix, elevation matrix, and this is my elevation data which I can store in the form of a DEM. But this elevation data can be represented in the form of the contours. I can use a certain threshold values in order to determine the contours. So between two values, I can draw within certain color. So different colors here are indicating those contours with the values and the range between those two values. So I can represent the grid matrix as elevation contours. I can also now, when I divide that area into the grid cells, I have to be a little careful in doing that, because the grid size also will determine the kind of features which I want to depict on the ground. So this example is showing me that if we select a 30 meter size of the grid, 30 meter by 30 meter or 10 meter by 10 meter or 3 meter by 3 meter grid size. So when the interpolation has been done from tin to grid model, interpolation has been done from 30 meter to 10 meter to 3 meter, we are getting the different information content from the digital elevation model. And certainly we can see that at 3 meter grid size we can see much more detailed information as compared to the 30 meter. Some information, particularly in this area, you will see the information got blurred, while we can see very clearly some of the artifacts and the linear features in this particular area. This digital elevation model which you are actually creating, you can superimpose on the top of the satellite image. So here it is the representation, how you are showing the DEM and superimposing on the top of it the satellite image. So one can see the green area which are the forested area and the snow covered area, and the peak of the ridge line and the valley line, they all can be seen. So, the visualization of the terrain, understanding the terrain is much easy to us with that kind of a figure. We have data sources for free DEM also. So, if we do not want to create a DEM, or if it is difficult or the aerial photographs are not available to us, then there are some data sources from where we can actually freely download the DEM and still can work in our area. So, these are the some sites here and some topographic. This is a space shuttle radar topographic mission, very popular, and it is called SRTM. SRTM stands for the Shuttle Radar Topographic Mission, and here at 30-meter resolution and 90-meter resolution, the DEM data is available. So, if you go to SRTM site, further details you can get there and you can actually download the data for your study area. The another device is ASTER, ASTER, which is called Advanced Spaceborne Thermal Emission and Reflection Radiometer, and also here you have the data for the entire globe. You have the global digital elevation data at 30-meter resolution. The third site is JAXA's Global ALOS 3D World at 30-meter. So, you can go to this site, JAXA site, and then download the data. The fourth one is GTOPO30, but this is a slightly crude kind of the resolution is 1 kilometer. So, a large area and few points you will see in this GTOPO30. And also we have global multi-resolution terrain elevation data, which is called GMTED 2010. So, these are few sites where you can get some global data available free of cost, but resolution will not be that high as we can get from our ground based methods. In India, we have a similar kind of a site called Bhuvan BHUA VAN. This is the Indian portal where we can get data from our own Indian satellites called Cartosat 1 and Cartosat 2 data, and DEM of certain regions can be actually freely downloaded at 2 to 3 meter resolution. So, some alternate means of creating the getting the DEM are available to us. So, this is for example the SRTM data, satellite data here. So, this is SRTM data, and you can see the catchment, and this is data has been downloaded from the sites, and here again you can see some dark areas and you can see some brighter area. The dark areas are those areas where the elevation is low. This is the ASTER-DEM, the another method of downloading the free from ASTER sites. This is the DEM in 2 dimension, and this is the DEM in the 3rd dimension, where you can see the peak of the mountain from the ASTER-DEM at 30-meter resolution. So, this DEM, in order to have the better visualization of the features, you can on the top of that you can drape the satellite image, so that you can have a better visibility of the ground and you can understand the ground in a much better way than from a topographical map or from stereo photographs. So, this is our GTOPO30 DEM at 1 kilometer spatial resolution. So, when you have the poor resolution, then the area covered becomes quite large, and you can see whole of the globe, and at different points you can get the different elevation values. So, it is good when we are doing some study related to the global level, like global climatic change and so on. There are various uses of the digital elevation model, DTM and DSM. So, we are using them, we are preparing them, and we are using them for planning schemes and development assessment scenario on the ground. Hydrological study, we cannot carry out any hydrological modeling study without the elevation data or without considering the capabilities of the DEM, because the slope or the elevation or the terrain relief is very important whenever we are dealing with any of the hydrological model. In a transport corridor planning, because we have to maintain a certain slope of the ground, and while we are having the curves, okay, vertical curve, the horizontal curve, again we have to see the super elevation and the gradient of the ground. So again the elevation is playing very important role. For soil erosion control and modeling, visibility analysis is another part, when we are planning something and we want to see how much area is visible from that particular location which is at a certain height or in the valley region, then we can do that visibility analysis from this DEM. Water management plans and subcatchment delineation can be done with the help of the digital elevation model. So delineation of the watershed was very difficult with the help of the contours, but nowadays we can do it automatically once we have digital elevation model. In all kinds of a disaster, whether it is related to the flood or it is fire, planning and the management, we require this data. For natural resource management, very important. Telecommunication planning is important. Tourism point of view, whether a tourist site is accessible and what is the slope, or whether this is at a certain height, what is the height of that point. Infrastructure planning, or whether we are talking of the smart city planning, where we would like to have not only DEM but we like to have the DSM. So these are some of the applications listed where we might require either DEM or DTM or DSM data in order to successfully work in that particular application. Now when you are visualizing the terrain, this is a very important area, visualization of the terrain right in the laboratory. So there is actually no need to go to the ground to see actually the terrain, to see the ups and downs in the terrain. Nowadays with the help of the visualization capabilities of the software, we can create the whole terrain in the lab itself, in the computer simulated environment. So terrain visualization, because any project planning would require reconnaissance of the terrain. So that can be done with the help of these tools nowadays. If we are doing hydrodynamic modeling or flood management plans we are developing, the DSM is very useful. As you can see, this is a hydrodynamic modeling approach which is shown. The blue is all that flood water which has entered into the urban built up area, and if I show you the blow up of some area, you can see the height of the structure also. So one can see that there are some buildings actually which are under the influence of the flood, which are submerged, partly submerged into the flood, and there are some areas where the flood has not reached. So depending upon the depth of the flood, one can carry out the study and find out which are the safer area. For example, these are the safer areas away from the river and situated at a certain height. So here the elevation is playing very important role whenever we are doing some kind of a hydrodynamic modeling. Representation of the area in the 3D visualization model. So you can create a 3D visualization model of your institute, of your school, of your building, of your house. So you can see the actual shape, orientation and actual size of the building, height of the building. So this height data is very now important to carry out the visualization of the work. Now people have actually created that kind of a visualization also with the help of the data which is collected at different times. You can see that the data has been collected at different times, and this particular diagram, this particular slide is showing at different dates how the construction is progressing in the area. So if you have the images of the area at different times of the construction, then this 3D model can be created in order to show it to the decision maker. There is no need that everybody goes to the site and see the actual progress. So this looking at the progress through the visualization model is quite popular now. Now this is a fly through model. You can create a fly through model. That means right sitting in the comfort of the office. Now what you can do is you can create a fly through model, and this will look like as if you are flying in the aircraft, and you can actually go through this particular model and see the feel the kind of a ground, what is how as you are flying through the aircraft and looking down to the area. This is a three-dimensional again representation of the flow of water. In case there is a rainfall here in the catchment, then you can see that how the rain water is accumulating at this particular point. So these kind of a spatial and temporal pattern when we are creating, it helps us to identify that how much time it will take actually water to reach downstream and how much quantity the water would flow. So all that the digital elevation model or DSM is playing very important role in order to understand this. This is about the visualization of the flood. So there is a river under the normal circumstances, you can see the flood in the river, but water in the river, but during the flood situation what is happening is the flood water would actually find out what is the steepest slope path. So these are the areas where the elevation is low. So water would actually flow in those areas first and try to damage the surrounding land. So whenever we have to carry out the planning to protect the area from the flood, then we have to understand in 3D which are those critical sites and areas where flood protection devices are to be planned. So this is all which I want to explain you that what is the utility of this DEM, DSM and DTM which we are creating using the capabilities of digital elevation model. Thank you.